In this video, we're going to learn some ideas about polygons and then also look at determining the perimeter of polygons. So first, just some vocabulary that matters so we're all speaking the same language. A polygon is an enclosed figure made up of 3 or more line segments. So it has to be at least 3 because you can't create an enclosed figure with less than that. And then line segments, they're all going to be straight sides, no curved sides on a polygon. Alright, some examples are triangles or quadrilaterals. So a triangle has 3 sides, a quadrilateral has 4 sides. The prefix quad means 4 and lateral means side. And so those are the couple we're going to focus on for the sake of this video. There are others, that's where you get hexagons and pentagons and things like that, dodecagons. Any of those, right now we're just shoving those all into the other category. We're going to focus a lot on quadrilaterals in this video, and then there'll be a separate video that focuses on triangles and so on. So let's just dive into focusing on some things about quadrilaterals. Okay, as I've already stated, quadrilaterals have 4 sides, and that's literally what the name means. Quad is 4, and laterals is sides, so it is a figure made up of 4 sides. Okay, if you have a quadrilateral, it have 4 sides, it's going to have 4 angles as well, and the measure of all those angles added up will be 360 degrees. It doesn't matter about the length of the sides, or whether it's a regular quadrilateral or not. All of its angles, the measure of all of its angles will add to 360 degrees. Okay, so now what we're going to do is name 5 different types of quadrilaterals. So all of these are quadrilaterals, they're just special names for 5 different types of quadrilaterals. Alright, the first one we'll look at are rectangles. With rectangles, all the angles of the quadrilateral will measure 90 degrees. That necessarily squares things out, and I want to be clear about this word square because the next quadrilateral we'll look at is a square, but we also use this word square for an angle, meaning it's 90 degrees. And so when you have 4 90-degree angles, all of your angles square out. I also want to emphasize before we go on to a square that a rectangle has no restrictions on the side lengths. So it doesn't say anything about the side lengths, it's just that all the angles have to measure 90 degrees. Okay, so then a square is a rectangle where all the sides are the same length. So here, what that means is that a square is a rectangle, but a rectangle is not necessarily a square. If you have all the sides are the same length and all the angles are 90 degrees, that thing is a square, and it's also a rectangle. But if you have a rectangle where all the angles are 90 degrees but the sides are different lengths, then it's not a square, but it's still a rectangle. Feels like a riddle, but it's kind of an important thing to wrap your brain around. Alright, we'll go ahead and move forward with the other 3 types, which are less known. I didn't draw pictures for these 2 types because most people feel like they have a sense of what a rectangle is and what a square is. It's just important to note what I said, where a square is a rectangle, but a rectangle is not necessarily a square. Now, the next one we're going to look at is a parallelogram. As far as what a parallelogram is, there's a hint in the name itself. Parallel is in the name, and the idea of what a parallelogram is that the opposite sides are parallel to each other. So the opposite sides are parallel to each other, and I'll try to draw some decent pictures here. Alright, I did cheat a little bit to use the computer to draw the picture for me, but I'll draw the other 2 just for the sake of demonstrating something. But this is the idea of a parallelogram. This side is parallel to this side, and this side is parallel to this side. Since I used the computer to draw this figure for me, you don't debate that too much. However, there's a way that we sketch in some notions that help us understand that it's a parallel, those sides are parallel whether or not it's drawn well. And we can say, we use these little tick marks to say that these two sides are the same length. And then I can put 2 tick marks on these sides to say they're the same length. We can do something similar with angles, so I can put a little swoop in for that angle and do a couple tick marks, and swoop this angle, a couple tick marks, or the smaller angles I can use 1 tick mark, and that's saying those opposite angles are equal in measurement. So if all of that is true, it forces the sides to be parallel. So there's so that's a way of saying, hey, these are parallel. And if the sides are all like the opposite sides are the same length, then it forces those opposite angles to also be the same measure, which forces the fact that it's parallelogram. So I'm just doing all of that to help you see how we kind of write things, so that even if the picture is a bad picture, we're still going to be dealing with parallelogram. So one of the things I want to emphasize, I'm going to draw in this picture, so I can't even draw a straight line segment, a perfectly straight line segment, but we use our imagination. Now what I have here, if I put a little square in each one of these corners, then I'm saying that that is a rectangle because all of my angles measure 90 degrees. And really I only need to put the square, I need to square out opposite corners or something like that, and then that induces the other two. But once I do this, and I'm told because of those little squares in the corner that this is supposed to be a rectangle, despite the artistry of it, then I also know that it's parallelogram because the opposite sides are going to be parallel in a rectangle. So a rectangle is also a parallelogram. So if I continue on in that way and I do my best right here to draw in what I'm aiming for as a square, I put in my right angles or my square angles. Okay, so I have something. Now that right there is not enough to say this is a square. It's enough to say it's a rectangle. But if I say the opposite sides are equal, and those are also equal here, now I'm definitely dealing with a square, but it's also a parallelogram. So a square is a parallelogram is a rectangle. Square kind of has a lot of, it's so perfect, it gets a lot of different labels that can be applied to it. So hopefully that gives you an idea of what a parallelogram is, and also how we can sketch up the figure to communicate to you that it's a parallelogram without saying, hey, here's a parallelogram. Our next one we're going to look at is a rhombus. Alright, so a rhombus is one that's probably not as well heard of. It's a parallelogram with equal side lengths. So if you think of, basically if it has equal side lengths, we're thinking of a square. But this is a little bit more dynamic than a square because it just needs to be a parallelogram. It doesn't have to be a rectangle. But it is true to note that a square is a rhombus. Square is a parallelogram. It's a rhombus. It's everything. Because if it's parallelogram and it has all equal sides, then it is also a rhombus. So there's my poorly drawn rhombus, but you shouldn't take it at face value drawn just like that, especially one that poorly drawn. But if I, put in my tick marks to say all my sides are equal, and then I say my opposite angles are, I shouldn't be using equal, I'm being a lazy person, but all my sides are of equal length and my angles are of equal measurement, then now, regardless of how poorly it's drawn, I know it's a rhombus. I don't really need these other angles because they're forced. Once the first ones are said to be the same measurement, then the other two are forced. I'll let you puzzle that out and convince yourself of that. But you can draw them all in for emphasis sake. So that's a rhombus. But remember, a square is also a rhombus, a parallelogram, and a rectangle, and so on. So a rhombus, a square is a rhombus, but a rhombus isn't necessarily a square. We're back to that little riddle. And so as you're learning these names, it's important to know them well enough to know which ones are inclusive in which directions. Alright, our next shape is going to be a trapezoid. Alright, so a trapezoid is a quadrilateral with exactly one pair of sides parallel to each other. It's kind of the odd guy out. A trapezoid is a trapezoid and nothing else is a trapezoid because of this word exactly. So it's not a parallelogram because parallelograms have two pairs of sides that are parallel to each other. It's not a square because a square has two pairs of sides that are parallel to each other. So a trapezoid is kind of its own thing. I'll draw a couple of examples. Alright, so the most stereotypical way a trapezoid is drawn is like this, maybe with some better artistry. But that sort of thing, it kind of looks like the peak of a house, but with the top cut off. But these sides here are the sides that are parallel, and this is a way of showing parallel that I haven't shown yet, but if you put the arrows on them like that, it's saying, hey, these are parallel. And then that's a trapezoid. But the sides that aren't parallel don't have to be in any way symmetric or reflections of each other. So for example, I could have something kind of like this. It looks like it's trying to be a parallelogram. These opposite sides are parallel, but the other two are not. And you might think, well, that's just because I'm bad at drawing these pictures, which I am, but without indicating that they're parallel, you can't assume that they're parallel, whether or not they look parallel. So a trapezoid doesn't have to be this nice, pretty, perfect, if looking thing. I know mine's not too perfect, but anyways, that's the stereotypical trapezoid, but it doesn't have to look like that. For it to qualify as a trapezoid, it just needs to have four sides, because it has to be quadrilateral, and two of those sides, exactly two of those sides, need to be parallel to each other, no more, no less. Alright, so those are the 5 names of quadrilaterals that you'll need to know, and you'll need to know how they're related to each other or overlap each other. So we've talked about polygons in general. We're going to address triangles and all the wonders of triangles in a separate video. Here we've emphasized some specific names for quadrilaterals, but now we're going to go back to polygons in general and talk about perimeter of polygons. Alright, so again, when I'm talking about perimeter, I'm talking about for all polygons, not just the quadrilateral names we just learned, not just triangles, all polygons. The way you find perimeter, okay, so first of all, what perimeter is just the distance around the polygon. So if you think about, like, if you're going to guard the perimeter of your compound, you're guarding around the outer edge. So perimeter is just that outer edge, and when we're finding the length of the perimeter, we're just taking the measurements of all the different side lengths and adding them up. So in general, the perimeter is the length around the outside of a figure. Now, we're going to talk about it in general with polygons, but it doesn't have to be a polygon. So that's not a polygon because it has a curved edge, but we could still talk about the perimeter of that shape. So this is the more generic idea of perimeter. It's the total length around the outside of a figure. But for polygon, we add the lengths of all the sides. Now this can be broken down into some obnoxious number of different formulas, but I don't think formulas for perimeter make any sense. You just add up all the lengths of the sides. So for example, the perimeter of a square would be the formula for S, where S is the length of one of the sides, but that creates a lot of memorization that isn't necessary if you just think I need to add up the length of all the sides. Let me do an example. Alright, so we're going to find the perimeter of the figure, and I tried to draw it somewhat to scale, but you shouldn't trust that when I'm sketching these figures. Just trust the labeling over the way it looks. So what we have here is, what we need to do here is add up the lengths of all the sides, but we're only given lengths for some of the sides. So we need to infer the lengths of these other two longer sides. And you just get that by reflecting it back to the far sides. And the reason why I know I can do that is because of all these right angles says that everything's squared out. So basically, let me clear out some of this highlighting. Since all those angles are squared out, the length of this side, the length of this side, can be reflected over to here. And so then that's going to tell us that this side is 3 and 4, which is 7 feet. I give the answer away so much. Similarly, we're going to get that this one's 9 feet. So hopefully you can see how we're reflecting that over. And you can't do that on just any old thing. We're able to do it here because everything's squared out, so it has to translate directly over. So then once I know all the side lengths, determining the perimeter is just a matter of adding up all those side lengths. And when I add them, I like to include the units, because if you include the units in your calculations when you're doing geometry problems and you understand how dimensions work, you won't have a mystery on what your units of your result would be. So we're going to add all those up, and we get 32 feet for the total length around the shape. Alright, and that's the idea of finding perimeter, and this really is kind of the hardest type of polygon to find the perimeter of, is when they don't tell you all the sides, so you have to figure out some of them by getting them off of the other sides. There's some harder perimeter problems when we start working in those curved edges, but before we can get to those, we've got to learn about circles. So you can just store that away as something exciting that's just yet to come. So go ahead and give some of these a try and see how you fare.